Alright, so let's talk about why we're graphing inequalities on these. The main reason is that in the real world we don't often have constraints that are saying you have to use exactly this much of a material or you have to use exactly this much time on a machine. Usually, most of the time, when you see real-world constraints, they take the form of inequalities. You can use no more than this much material, or you can have no more than this much time on the machine, or you have to produce at least this much of something. Those words, no more than, less than, or sorry, no more than, no less than, or more than, those translate into inequalities. So let's look at this example. We have a small pottery shop that produces two kinds of planters. Each glazed type requires a half hour to throw on the wheel and 1 hour on the kiln. And each unglazed type takes 1 hour to throw on the wheel and 6 hours in the kiln. The wheel is available at most 8 hours a day, and the kiln is available at most 20 hours a day. So you can see these words at most and at most. These are restrictions, and another way of saying that is constraints. And these end up being, we would end up translating these as inequalities. So first off, the wheel. The wheel has a restriction. It says we can't use the wheel for more than, we have to use it less than or equal to 8 hours a day. It can be used at most. That means we can use it less than or up to exactly equal to 8 hours. So we need to figure out the total amount of time that the wheel is used. Well, we're making two kinds of planters here. Let's give these some variables. The number of glazed planters I'll call X, and the number of unglazed planters I'm going to call Y. Because we need to be able to refer to, if I'm making 6 unglazed or 6 glazed or something like that, I need to be able to give those names. So the glazed type requires a half hour to throw. It also requires some time in the kiln, but I'm talking about the wheel right now, so I don't really care how long it takes in the kiln at the moment. I'm only caring about the wheel, since that's what this restriction is about. So the glazed type takes a half hour to throw on the wheel. Well, if you figure out the total amount of time that we're spending on glazed planters, we have a half hour per planter times, well, however many planters there are, which we decided to call X. We can do the similar sort of thing for the unglazed. For the unglazed, it takes 1 hour on the wheel. I don't really care how long it takes in the kiln right now. So 1 hour per unglazed times the number of unglazed. So this right here is the time spent on the wheel for glazed planters. This one is the time spent on the wheel for unglazed planters. And in total, well, if we add those two values together, this would be the total amount of time spent on the wheel. We know that the amount of time spent on the wheel needs to be at most 8 hours. So this number, whatever it is, it needs to be less than or equal to 8 hours. This is our first inequality. The second inequality here is, I'll make this one the amount of time at the kiln. And again, I'm going to look to see how much time is taken at the kiln, in the kiln for the glazed type. Each glazed type requires 1 hour in the kiln, so I'm going to say 1 times X for the total number of hours that the kiln is used for the glazed planters. And the unglazed, looks like they each require 6 hours in the kiln, so I'll say 6Y. And the kiln is available at most 20 hours a day, so I'll say 1x plus 6y is less than or equal to 20. Again, less than or equal to because we said at most 20 hours a day. So at first glance you might think that, okay, this is good, these are all the constraints that are that make sense here, but there actually are two additional ones. And this kind of goes back to, well, you kind of have to kind of reason your way through these. They're not actually stated in the problem. And I'll put it to you this way. Is it possible to make a negative number of glazed planters? Well, of course not. I can't make a negative number of them. Would it be possible to make 0 glazed planters? Well, yeah, I could make 0. So what I'm going to do to express this is say that x must be bigger than or equal to 0. Similarly, y must be bigger than or equal to 0, because I can't make a negative number of unglazed planters either. So we end up with 4 inequalities here, and this is our system that we're being asked to graph. Of course, the x is greater than or equal to 0 and y is greater than or equal to 0. Those are pretty easy. We can take those into account just by saying that we're restricted to the first quadrant here. So when we graph those, that's all we need to do. Just keep it in the first quadrant. To graph the other ones, the other lines, I'm going to use the x and the y-intercept. I'll say what happens when x is 0, and then what happens when y is 0. First off, when x is 0, that part goes away. I get 1y equals 8, which means y equals 8. And when y is equal to 0, that's what this one says, if that part goes away, I get 1/2 x equals 8, in which case multiply both sides by 2 to get x equals 16. Alright, for this one, I can do this same sort of thing. When x is equal to 0, I get 6y equals 20. Divide both sides by 6, which gives me 3 1/3, I suppose. 3.3 repeating. And then when y is equal to 0, that part goes away. I get 1x equals 20. Oops. I get 1x equals 20, which says that x equals 20. So it's not going to let me undo that. Yeah, whatever. I get 20, 0. Okay. So you'll notice it's a good idea I decided to find these points before I started deciding the scale here, because if I had decided that this only goes up to 10, I wouldn't be able to graph that intercept or that one. Instead, what I'm going to do is I'm going to go ahead and say these go in steps of 2. That way I go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And similarly, 2 all the way up to 20. Just labeling some points, so labeling some scale, just enough to find my way around. I did the 2 on here just because I like doing that, because then it shows you how big each step is without kind of having to figure it out yourself. Alright, so the first line, we have a y-intercept of 0, 8, which is right there, and the x-intercept of 16, 0, it's 12, 14, 16. So that looks about like this. Testing the point 0, 0, because it doesn't go through the origin. I can use 0, 0 as a test point. I get 0 plus 0. I'm plugging stuff into this equation. 0 plus 0 is less than or equal to 8. That means the origin satisfies this, and actually if you kind of think about what this equation is saying, this equation is ensuring that we're not overusing the wheel, the throwing wheel here. If we produced 0 pots of either type, we're certainly not going to overuse the wheel, which means that we would be restricted to the side of the origin. So that's kind of what's showing up here. Let's see, for the kiln, we have the point 0, 3.3 repeating. 3 is there, 3.3 repeating is going to be just a skosh higher. And then 20, 0, which is over here. Let's go ahead and draw a line that goes through those two. It looks about like that. And again, if we produced 0 of both planners, we're not going to overuse the kiln. 0 plus 0 is less than or equal to 20 is a true statement, so we're going to shade again toward the origin. So taking all of these into account, we need to be to the left, or to the right rather, of the y-axis. We need to be above the x-axis, and we need to be below both of these lines. This is the region we're talking about right here. Notice it doesn't continue past this line, so if I was able to zoom in there, well, I can zoom in a little, I guess. You can see I'm stopping at that line. So this would be the graph of these inequalities.